Hello everybody, I'm Gaëtan Klein here from the Institute for the Study of Pig States, and in this video I'm going to break down a new study that just came out about sperm remembering non-DNA coded traits to embryos. So I'm just going to read the article to you and comment it and link it to our discoveries on epigenetics and the transmissions of emotions, lifestyle and other elements of our cells to our offspring. So let's go right into it. So this article was published just a week ago in this magazine, and you can find it in this URL here on sciencealert.com. We know how sperm remember and pass on non-DNA coded traits to embryos. And here you have a picture on electron micrograph of a sperm cell. So what it means, what this title means, is that the sperm can carry information that are transmitted to the embryo that are not genetic information. So there is a memory beyond the genes. Studies in mammals have shown that the memories of various environmental effects, such as diet, weight, and stress, can be passed on from fathers to offspring, despite these effects not being coded in for the DNA sequences carried by the sperm. So what does that mean? It means basically that as a father, you transmit to your offspring your genes, but also your lifestyle, right? What you eat, how much you're weighing, how much stress you're under, all of this can be transmitted to your offspring, so it's really important. It's not just basic and strict DNA, but it's something else. Thanks to a 2021 study, we have an explanation for how it's possible. The story has much to do with epigenetics. That's what we study. Molecules that attach themselves to DNA can act like on-off switches that control which section of DNA gets used. But until 2021, we didn't know which of these molecules can carry the settings marked by a father's life experiences to be incorporated into an embryo via sperm. The big breakthrough with this study is that it has identified a non-DNA based means by which sperm remember a father's environment, in this case the diet, and transmit that information to the embryo, said Sarah Kimmins from McGill University. She's an epigenetist, and she was describing this study using mice. Epigenetist Ariane Lismer and colleagues were able to demonstrate that the effects of a folate deficient diet could be passed on by altering histone molecule in sperm. Simply put, histones are really basic proteins that DNA wins around for tangle-free storage. So that's exactly what we found, that we discovered a few years ago. You have your genes, and around the genes you have those molecules called histones. And those histones allow the genes to open up or to close and open and close. And you need the histones to open themselves so that the genes can be expressed. If the histones stay closed, you cannot use the information from the gene. So you cannot use the biological ability of the gene. In mammals, when male body builds sperm, they throw out most of the histone spools to allow for tighter packing. But a small percentage still remains, 1% in mice and 15% in humans, providing scaffolding for DNA in regions specific to sperm creation and function, metabolism, and embryo development, to allow the cellular mechanism to make use of these DNA instructions. What that means is that basically it's the histones that decide if you can use the instruction from the DNA or not. And those instructions are fundamental to metabolism, sperm creation, embryo development, etc. Chemical modification of these histones, the most common form being methylation, is what allows or prevents the DNA to be read so that it can be transcribed into protein product. Poor diet can cause these histones to change their methylation status. So if you eat bad food, if you don't have a good diet, those histones change. And that means that the genetic expression changes. The DNA can or cannot be read. And this is why we hear about the importance of folate for women during pregnancy. a mother's folate helps stabilize DNA methylation in their young. So that's really interesting because it's been pretty much common sense nowadays that when you are a mother carrying a fetus, you need to take a lot of vitamin D and especially folates to help the baby. We thought previously that it was because the vitamins are transmitted to the baby, but there's something that happens even before you're pregnant. If you have a lot of those vitamins in yourself and you have a good diet, this strength in your epigenetic factors is also transmitted to the baby when you become pregnant. But even more interesting is that it's also true for the father. So if you, as a male, has a deficiency in folate, that increases the risk for the baby to have issues. And that's exactly what they say. By feeding male mice a folate deficient diet from the time they were weaned, the researchers were able to track the changes to histones from the male sperm and in the resulting embryos. And indeed, sperm histone changes were also present in the developing embryo. Yes. So if you, as a father, have a poor diet, you also increase the chances of your baby to have an impaired health, so to speak. No one has been able to track how those heritable environmental signatures are transmitted from the sperm to the embryo before, said Lismer in 2021. The team also discovered these effects could be cumulative and lead to an increase in the severity of birth defects. Interestingly, the birth defects seen in mice, including underdevelopment at birth, spinal abnormalities, are well documented in folate-deficient human population. Yes, so that's what I was saying. But it's not just the mother who has to take folates to protect the baby against these issues, the father too, because it's transmitted through epigenetics. So researchers hope that expanding our knowledge of inheritance mechanism will reveal additional ways to treat and prevent such condition. Well, you can prevent the problem by having a good diet, right? But also, in a more general fashion, a good lifestyle, a healthy lifestyle. But there is a lot more work to be done out there. Our next step will be to determine if these harmful changes induced in the sperm proteins, the histones, can be repaired. We have exciting new work that suggests that this is indeed the case, said Kimmins. So this research was published in Developmental Cell, and there was the first version of this in March 2021, so a year and a half ago. So this is exactly what we at the Institute for the Study of Pig-Sets have been saying for years. Actually, this is exactly what we describe in this book, Subcellular Psychobiology by Dr. Grant McFetridge. And this book was published in 2014, so 8 years ago. And we describe how epigenetic damages are transmitted from parents to their offspring and in the form of psychological traumas and other form of biological damages. And actually it stems from the work that was done previously by Grant McFetridge and the Institute, published in Pig-Sets of Consciousness Volume 2. And that book is even older. I think this book is from 2008. That's right, 2008. So 14 years ago, that's what we were saying. Epigenetic damages are transmitted from the parents to their child. And there are other researchers that will publish on this channel later, but we know scientifically that emotional shocks and stress and emotions are transmitted from parents to their offspring, but also they carry on from for multiple generations. So if your grandparents had stress, you also carry that stress in your epigenetic damages, and not just your parents and your grandparents, but the generations before. So all of these generational issues and stresses can be transmitted to the fetus. That's what we call generational traumas. So if you're interested in learning more about this, I have more videos on my YouTube channel about epigenetic damages and psychobiology and how it works. So under this video, you will have the link to other videos and you might see them popping up right now. If you liked this video where I discuss new scientific findings, please leave me a comment and like it, and I will do more. Thank you, and I see you in the next video. Thanks.